When an archaeologist unearths a bone or a wooden tool from the soil, it doesn't come with a manufacturing stamp. There are no calendars, no written records, and no historical witnesses to tell us when this creature lived. So how do scientists assign an exact age to an object that has been buried in silence for thousands of years? Hidden inside the relic structure is a microscopic timekeeper. This Atman Kigati, or atomic clock, formed during the high-energy collisions of outer space. To read the deep history of humanity on Earth, we actually have to look up, straight into the subatomic debris raining down from the cosmos. High above our heads, Earth's upper atmosphere is under constant bombardment. High-speed protons, known as cosmic rays, travel across deep space and slam into our atmospheric barrier, shattering the gas molecules they hit. These collisions break apart the stable atoms in the air, sending tiny, high-speed particles called neutrons flying off in every direction. This diagram shows what happens next. The air we breathe is about 78% nitrogen-14. When a stray neutron crashes into one of these nuclei, it forces its way inside, and a single proton is ejected. By losing that proton, the nitrogen atom transforms. It is now a radioactive isotope known as carbon-14. Because this cosmic rain never stops, the Earth is supplied with a continuous, invisible supply of these radioactive timekeepers, drifting high above the clouds. This carbon-14 quickly bonds with oxygen to form radioactive carbon dioxide, which plants absorb during photosynthesis. Humans and animals graze on those plants, incorporating carbon-14 directly into their bones and tissues. As long as a creature is alive, eating, and breathing, its internal supply of carbon-14 remains constant, perfectly matching the ratio in the environment. The clock begins to tick the moment the creature dies. Breathing and eating stop, cutting off the supply of new carbon from the atmosphere. Inside the remains, carbon-14 is unbalanced, with 6 protons and 8 neutrons. Driven by the weak nuclear force, an excess neutron transforms into a proton for stability. The nucleus ejects a beta particle and antineutrino, reverting to stable nitrogen. Death isolates the organism from the world, turning its remains into a decaying hourglass that slowly empties its carbon-14 atoms over thousands of years. We measure the speed of this hourglass through its half-life. For carbon-14, it takes exactly 5,730 years for half of the atoms in a sample to decay. This chart shows the progression. If a bone starts with its full amount of carbon-14, exactly 50% remains after 5,730 years. After another 5,730 years, that amount halves again, leaving only 25%. By measuring the faint beta radiation emitting from a sample in a lab, scientists trace this math backward to find the exact millennia the creature died. Carbon dating has a limit. It loses its accuracy for any artifact older than roughly 50,000 years. By this point, the carbon-14 has halved so many times that the remaining amount is nearly undetectable. The hourglass is empty. This method also requires biological matter. It cannot be used to read the age of inorganic materials like rocks or the Earth itself. To measure deeper time, the age of the dinosaurs or the birth of the planet, scientists must look for a clock with a much slower tick. That deep time clock is uranium-lead dating. It follows the same logic of radioactive decay, but operates at a glacial pace. Unstable uranium slowly sheds its excess mass until it settles into stable lead, a process with a half-life of 4.5 billion years. Researchers use this uranium clock to test meteorites, pristine space rocks left over from the formation of the solar system. Based on the ratio of uranium to lead in these rocks, we know that the Earth and our solar system are 4.5 billion years old. As Carl Sagan observed, we are made of star stuff. By measuring the decaying atoms within ourselves and beneath our feet, we are reading the literal history of the universe. Subscribe to Divine Gurukul to keep exploring the science of our cosmos.